Today we start about recursion formula. Given infinite subset C of Z plus, there is an unique function h Z plus to C satisfying the formula h1 equal to smallest element of C and hi equal to smallest element of C minus smallest element of C minus h of 1 2 I minus 1. Okay, for all I greater than 1. Now this formula star, we denoted it by star. Then this star is called, the formula star is called is recursion formula. The formula star is called the recursion formula. Now recursion formula for h. Okay. Next, it defines the function h in terms of itself, and a definition given by such formula is called recursion definition. A definition given by such formula is called recursion definition. Okay. Now we also see that the recursion formula hi equal to smallest element of hi equal to smallest element of C minus h of 1 2 m I plus 1. Okay, this is the recursion formula. For example, is self-contradictory. For example, itself, the recursion formula this is self-contradictory. Okay. This formula says that it does not belong to the set. This formula says that it does not belong to the hi is an element of the set which does not belong to the set. Okay. hi, this formula says hi belongs to set, hi necessarily an element of set, where hi smallest element of these. It defines although hi necessarily is an element of set this formula says that it does not belong to the set. Hi belongs to the set h 1 2 I plus 1, but here this formula says that it does not belong to the set. This formula says that it does not belong to the set. Does not belong to the set. Okay. Now we define principle of recursion definition. It is totally Now principle of recursion definition. Okay, principle of recursion definition. Okay, let A be a set. Let A be a set and given a formula that given a formula that defines H1 as a unique element of A, that defines H1 as a unique element of A, and for I greater than 1, and for I greater than 1 defines Hi defines Hi uniquely as an element of E. Hi uniquely as an element of A in terms of the values of H, in terms of the values of H for for positive integer less than I, for positive integer less than I. This formula defines a unique function. This formula defines a unique function. A unique function A z plus 2a. Okay. Then Hi uniquely as an element of A in terms of the values of H for positive integer less than I. Okay. This formula determines a unique function A z plus 2a. Then given this one is a formula. Now we start about one corollary. Okay, one important corollary we deduce from this theorem. A subset of a countable set is countable. A subset of a countable set is countable. Suppose a subset of B where B is countable. Where B is countable. There is an injection F of B into Z class. There is an injection F of B into Z class. The restriction of F to A is an injection of A into Z class. Okay. The restriction of B of F, the restriction of F to A, okay, is an injection of A into Z class, of A into Z class. Okay. Now we start. Then what we find? We find a subset of countable set. That means B is countable. Then A, B, down for you. Okay. Now, we're going to further we erase this portion and also start from a corollary also. Corollary. Okay. The set Z plus is countably infinite. Now it suffices to construct an injective mapping. It suffices to construct an injective mapping if z plus Cartesian product z plus to z plus. We define f by function. We define f by equation f of nm equal to 2 to the power n 3 to the power n, where nm belongs to z plus, z plus. Okay. Now we show that f is injective. Then this one is countably infinite. Okay. Now we show that f is injective. To show f is injective. For suppose that 2 to the power n 3 to the power m equal to 2 to the power p 3 to the power q. If n less than p, then 3 to the power m equal to 2 to the power p minus n 3 to the power q, contradicting the fact that that 3 to the power m is God for all m. Therefore, p minus n equal to 0. This implies p equal to n. Now this result going to 3 to the power m equal to 3 to the power q. This implies if m less than q, it follows 1 equal to 3 to the power q minus n. Okay. Then we going to a contradiction. So m equal to q. So m equal to q. Okay. Now z class Cartesian product z class is countably infinite. This now we're going to further proceed. We also erase this portion. Now example 3. Now start example 3, which show that q plus the set of positive rational number is countably infinite. Okay. Now we define a surjection. We define a surjection G z plus Cartesian product z plus to q plus by the equation g of nm equal to m by n, because z plus Cartesian product z plus is countable. There is a surjection. If z plus to z plus Cartesian product z plus, then the composite function, g naught f z plus to q plus is a surjection. So that q plus is countable. Of course, q plus is infinite because it contains z plus. Of course, q plus is infinite because it contains z plus. So we discuss about q plus is countably infinite. Now we're going to a countable union of countable set is countable. We show that we erase these things. Then we show countable union of countable So we show that a countable union of countable set is countable. A countable union of countable sets is countable. Okay. Then then what we do? We do let A n be an index family of countable set. A n belongs to J. Be an index family of countable set. Where the index set J is where the index set J is either 1 2 n or Z plus. Assume that each set A is non-empty. Assume that each set Jn is each set An is non-empty. For convenience, this assumption does not change anything. So, because if each An is countable, then we can choose each An is countable, we can choose for N, we can choose for N, for each N, we can choose for each N a surjective function, Fn Z plus 2An. Similarly, we can choose a surjective function G Z plus 2An, Gz plus 2J. Now define H Z plus Cartesian product Z plus 2 union of n belongs to J A n by the equation HKM equal to f of GKM, then it is easy to show that H is surjective. To show H is surjective. Since Z plus Cartesian product Z plus is in bijective correspondence with Z plus, Z plus Cartesian product Z plus is bijective correspondence with Z plus, then the countability of union follows theorem. That means B is count. That means this union is countable. Okay, union of AN is countable. Then union of AN be countable. Okay, that means start from this. We start from an indexed family of countable set where J is either 1 to n or Z plus, and assume that is a non-empty. Then an countable means a surjective function fn Z plus to an. Similarly, we can choose a surjective function G Z plus to a J. Now we define a Z plus Cartesian product Z plus to union of n belongs to J. A. By the equation HKM equal to f of GKM, to show that H is surjective, since Z plus Cartesian product Z plus is in bijective correspondence with Z plus, then union of AN is countable. Okay, so a countable union of countable set is countable. Now a finite product of countable set is countable. Okay, now we prove a finite product of theorem. A finite product of countable set sets is countable. Now we first let us show that the product of two countable sets, that means AB, we show AB countable, then to show A Cartesian product B be countable. If A or B be empty, then the result is trivial. Choose surjective functions. Choose surjective functions fz plus to a and gz plus to b. Then the function h z plus Cartesian product z plus 2 a Cartesian product b defined by the equation h n m equal to f n g n is surjective. So that a Cartesian product B is countable. Okay, then we start about further. That means if a n, that means if a1, a2 dot 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 an are countable, then 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 a1 Cartesian product a2 Cartesian product a and minus 1 be countable, and an also countable. So this be countable. Okay. Now if we define in this way, then this one is possible. Otherwise, we draw some G A1 Cartesian product A2 A1 Cartesian product AN minus 1 Cartesian product AN. Then defined by g of x1 x2 dot 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 xn equal to x1 x2 xn. Okay, then this set is countable. Since this one is countable and an is countable, then product of these two sets is countable. So we conclude that a1 a2 an minus 1 an is countable. So today stop here.